Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're covering solvation, solubility, and aqueous solutions. These are fundamental ideas in chemistry. So in this lesson, I want us to build a clear conceptual understanding of what it actually means for something to dissolve. To begin, let's define what a solution is. A solution is a homogeneous mixture, which means it appears completely uniform throughout. Even though multiple substances are present, you're not going to be able to distinguish them visually. On the molecular level, however, each component is still there. It's just thoroughly mixed together. Within that solution, we define two distinct roles, the solvent and the solute. The solvent is the substance that determines the phase of the solution. It's usually the component that's present in the greatest quantity. If water is the solvent, we call the solution aqueous. If the solvent is a gas, then the overall solution is considered gaseous. The solute, on the other hand, is any substance that is being dissolved into the solvent. It might be an ion, a molecule, or even a single atom, depending on the context. No matter its form, the solute is the component that's present in a smaller amount, and it is the one that becomes distributed throughout the solvent. Now, when a solute enters a solvent, it doesn't just disappear. What actually happens is that the solute becomes uniformly dispersed, meaning that its particles spread evenly throughout the mixture. The reason this occurs and why it matters is due to intermolecular interactions. These are the forces that govern how different particles attract, repel, and stabilize one another in a solution. And that brings us to a key concept, solvation. Solvation is the process in which solvent particles surround solute particles and begin to interact with them electrostatically. For solvation to occur, the original interactions between solute particles, those have to first be disrupted. Likewise, some of the interactions between solvent molecules must also be broken. Only then can new interactions form between solute and solvent. And this molecular reorganization is what allows dissolution to happen and for a stable solution to form. Now, going back to our scenario where water acts as the solvent. In this case, we refer to this process as hydration. That is because your solvent, water, will interact with your solute in solution. And you'll see this term frequently when discussing ionic compounds dissolving in water, because water's polarity plays a really key role in stabilizing charged species in solution. Now that we've established what a solution is and how solvation works, we can start to introduce a more quantitative concept, and that concept is solubility. Right now, we're just going to define solubility, and then later we're going to bring in the mathematics that describes it. Solubility refers to the maximum amount of solute that can dissolve in a given quantity of solvent at a specific temperature. From there, we can begin to classify different types of solutions based on how much solute is actually dissolved relative to the solubility limit of that solution. The solubility limit is simply the maximum amount of solute that can dissolve in a solvent at a given temperature before any extra solute just stays undissolved. Let's start with a solution that has not yet reached the maximum amount of solute that can dissolve. This is called an unsaturated solution. And in an unsaturated solution, the solute concentration is below the solubility limit at a given temperature. This means that technically more solute can still dissolve. On the other hand, when the solution reaches the point where no more solute can dissolve, we say that the solution is saturated. In a saturated solution, the solvent holds the maximum amount of solute that it can dissolve at that temperature. Now, if you went ahead and you added any additional solute, it's going to simply remain undissolved and it's going to settle at the bottom. There is, however, a special and less stable case we do need to consider, and that is supersaturated solutions. A supersaturated solution contains more dissolved solute than the solvent should be able to hold under normal conditions. And this situation can only be achieved by manipulating temperature. And it's important to note that it's not very stable. A small disturbance like stirring can actually cause that extra solute to crash out and precipitate almost instantly. These three categories, unsaturated, saturated, and supersaturated, give us a framework for understanding what kind of solution we're working with and how close it is to its thermodynamic limit. But there's another layer of complexity that we need to address. What happens to solute particles once they're dissolved? Specifically, we need to ask whether they stay as intact molecules or whether they dissociate into ions. And this question leads us directly to the concept of electrolytes. Electrolytes are substances that produce ions when they're dissolved in water. And the presence of these free-moving charged particles allows the solution to conduct electricity. But not all electrolytes behave the same way. So let's discuss strong electrolytes, weak electrolytes, and non-electrolytes. We're going to begin with strong electrolytes. A strong electrolyte dissociates completely into ions when it dissolves. That means essentially every formula unit separates into cations and anions, and the solution becomes highly conductive. Examples include soluble ionic salts like sodium chloride, strong acids like hydrochloric acid, and strong bases like potassium hydroxide. The key point is that these substances do not remain as intact molecules. They fully separate into ions, and those ions are free to move throughout the solution. As a result, solutions of strong electrolytes, they're highly conductive since the freely moving ions can carry electric current efficiently. Now let's compare this to a weak electrolyte. A weak electrolyte only partially dissociates in water. Some of the solute exists as ions, while some remain intact. And this equilibrium between dissociated and undissociated forms limits how much current the solution can carry. Now, classic examples are weak acids like acetic acid and weak bases like ammonia. Even though they dissolve somewhat in water, they don't completely ionize. So as a result, their solutions only have moderate conductivity. Finally, we have non-electrolytes. A non-electrolyte dissolves in water, but it does not dissociate into ions at all. The molecules, they remain intact, and this means that the solution does not conduct electricity. Examples include common molecular compounds like sugar or ethanol. These substances, they can be highly soluble, but their lack of ion formation classifies them as non-electrolytes and as non-conductive. Now, understanding the behavior of strong, weak, and non-electrolytes really helps us predict how a solution will behave, not just in terms of chemical reactivity, but also in terms of physical properties like electrical conductivity. Now, it becomes important to learn which compounds actually dissolve in water in the first place. And this brings us to the concept of solubility rules. There are 7 essential solubility rules we need to know that will help guide us in identifying whether something is soluble or insoluble. Before I tell you those rules, however, I want to clearly describe what insoluble means and then also describe the driving force for solubility. First, when we say a compound is insoluble, what we really mean is that it's sparingly soluble. These compounds do not dissolve to a large extent, but they do dissolve ever so slightly. There's always a small concentration of ions present in solution, and this small amount is enough to set up an equilibrium. That's why we can still define a solubility product for these salts, because they do solubilize, just in very small amounts. We're going to get to this in a few pages, but for now, I want you to keep this detail in mind. Second, it's important to understand why something is soluble. The driving forces here are lattice energy versus hydration energy. When the attractions between ions in the solid lattice is too strong to be overcome by solvation, then the compound stays undissolved. But when solvation wins, the ions disperse freely and the salt is soluble. Now, for our rules, rule number 1, all salts containing group 1 cations and ammonium are soluble in water. This is an easy starting point. If you see sodium, potassium, or ammonium in a salt, you already know it will dissolve. Rule number 2, all salts containing nitrate and acetate ions, anions, are soluble. Rule number 3, most halides, specifically chloride, bromide, and iodide, are soluble. The major exceptions are when these halides are paired with silver, Ag+1, lead, Pb2+, or mercury 1. So this is Hg2 with a charge of 2+. These ions form insoluble salts with halides. Rule number 4, sulfates are generally soluble, but there are key exceptions. Calcium, strontium, barium, and lead all form insoluble sulfates. Rule number 5, metal oxides are almost always insoluble, with the important exception of those formed with alkali metals, ammonium, calcium, strontium, and barium. Many of these oxides hydrolyze to form soluble hydroxides when they're placed in water. Rule number 6, hydroxides are typically insoluble unless they come from group 1 metals or the same subset of larger group 2 metals. That means calcium, strontium, and barium. Rule number 7, finally, the polyatomic ions, carbonate, phosphate, sulfide, and sulfite are all insoluble unless they are paired with group 1 cations or ammonia. For these, you want to develop the skill of prediction. So when you look at a reaction in aqueous solution, you should be able to anticipate whether the product will be soluble or whether a precipitate will form. And that prediction depends entirely on your knowledge of these solubility patterns. This is a skill that develops with practice and repetition, and my recommendation is just that. You won't be able to do any of the problems we tackle in this lecture if you cannot identify soluble and insoluble salts. With that, let's go ahead and jump into a practice problem. This one says, what is the precipitate that forms when calcium nitrate and potassium carbonate are added to water? Precipitate means what is the insoluble compound that forms here. So when we see this, the first thing we want to do is we want to break everything into ions. Calcium nitrate gives calcium 2+ and nitrate -1. Potassium carbonate gives potassium plus carbonate 2-. And now I want to pair the ions to see which combinations could form. Nitrates are always soluble, so both calcium nitrate and potassium nitrate stay dissolved. Group 1 salts like potassium carbonate, those are also always soluble. That leaves calcium with carbonate. According to the solubility rules, carbonates are insoluble except with group 1 and ammonium. Calcium is not an exception here, so calcium carbonate is going to form an insoluble salt. And that means the correct answer is calcium carbonate. The next thing we want to move into that's important and will be based on solubility rules and how to apply them, is the construction of net ionic equations and the calculation of solubility product constants, or KSP. We're going to begin with net ionic equations. First, I want to define precipitation reactions. A precipitation reaction happens when two soluble ionic compounds in aqueous solution react to form an insoluble solid. That solid is called a precipitate, and it separates from the solution as a solid phase. This is what we saw in the practice problem we just tackled. We had two soluble ionic compounds react to form products. Our goal was to identify what precipitate forms. So in other words, what the insoluble compound was, and we determined that it was calcium carbonate. Recognizing when a precipitate forms is key because that's the driving force behind writing appropriate net ionic equations. Let's figure that out by working through a classic precipitation reaction. Silver nitrate reacting with sodium chloride. To fully understand what's happening, we're going to write this process in 3 steps. Step 1 is the molecular equation. This is going to show all of the reactants and products in their full, undissociated forms. For example, we could write silver nitrate plus sodium chloride, both in aqueous phase. This results in silver chloride being formed and sodium nitrate. This gives us the reaction. We know that these are our products because in aqueous solution, the positive ions from one compound can pair with the negative ions from the other. So here, silver cations from silver nitrate, those can combine with chloride anions from sodium chloride to then form silver chloride. Similarly, sodium cations can pair with nitrate anions to form sodium nitrate. Step 2 is to write the total ionic equation. So now we're going to represent strong electrolytes as dissociated ions because that is how they exist in aqueous solution. So according to our solubility rules, silver nitrate, sodium chloride, and sodium nitrate are all soluble and are also strong electrolytes. So we can write them as free ions. That's what you see right here. Notice that we did not dissociate the silver chloride on the product side. That is because it's insoluble. It is a sparingly soluble salt. It forms a precipitate, and precipitates are written as solids, not as dissociated ions. Now we can move into our final step. Step 3 is writing the net ionic equation. To get this, we're going to eliminate the spectator ions. These are ions that are going to appear unchanged on both sides of the equation. So in this case, sodium cations and nitrate anions are the spectator ions. They appear on both sides, so we are going to eliminate them. What remains is the actual chemistry taking place. This is going to be our silver cations plus our chloride anions on the reactant side, both in aqueous phase. Those produce our product, silver chloride. This is our precipitate, so it's in the solid phase. This is the net ionic equation, and it tells us exactly which species are reacting and what is being formed. Silver ions combine with chloride ions to form a solid precipitate of silver chloride. Net ionic equations, they're useful for several reasons. First, they isolate the actual chemistry that's happening by removing non-reacting species. Second, they help us see the driving force of the reaction. In this case, that's the formation of an insoluble solid. And third, they allow us to recognize patterns across many different reactions. Once you learn to write net ionic equations, you're going to start to see that many aqueous reactions follow the same structure even when the compounds involved are different. Now, this particular reaction, it helps us introduce an important concept in equilibrium chemistry, and that is the idea of solubility product, or KSP. Even though silver chloride is classified as insoluble, a more appropriate term is sparingly soluble. That means a very, very small amount of silver chloride still dissolves, and it establishes an equilibrium between the solid and its dissolved ions. So in aqueous solution, this equilibrium looks like silver chloride can dissociate into silver cations and chloride anions. Because this is a reversible equilibrium, we can actually write an equilibrium expression based on the law of mass action. This gives us the solubility product constant. We can write KSP is equal to the concentration of silver ions multiplied by the concentration of chloride ions. Notice that we do not include solid silver chloride in this expression. Solids and liquids do not appear in equilibrium constant expressions because their concentrations are constant and they do not affect the position of equilibrium. Now, you might be wondering, if the original chemical reaction was precipitation, where silver ions and chloride ions formed a solid, why is KSP written for the reverse direction? And that is an excellent question. In practice, chemists are almost always interested in how much of a solid dissolves, not how readily it precipitates. So rather than define an equilibrium constant for the precipitation process, we flip the perspective and we write the equilibrium KSP for dissolution. If we were to define KSP as 1 over the concentration of silver cations times the concentration of chloride ions, that would give us a large, unhelpful number with poor predictive power. By writing instead the reaction from the perspective of dissolution, we get a small, experimentally useful constant that directly connects to ion concentrations at equilibrium. And that is what we define and what we use to define KSP. So in short, for sparingly soluble salts, chemists define the equilibrium constant in terms of the dissolution process, not the precipitation process. That is why we rewrote our expression to demonstrate the dissolution process first, and then we wrote the KSP based off of that. Now that we've defined KSP, we can use it to determine whether a solution is at equilibrium. To do this, we calculate something called the ion product, abbreviated as IP. This is essentially the reaction quotient for a dissolution process. Same concept, different words. Scientists are annoying like that. But anyway, the ion product is calculated using the same form as KSP. So it's the product of the ion concentrations raised to their stoichiometric powers. But unlike KSP, which is fixed at a given temperature, IP represents the current state of the system. And then by comparing the ion product to KSP, we can determine whether a solution is unsaturated, saturated, or supersaturated. If the ion product is less than KSP, the solution is unsaturated. This means more solute can dissolve until equilibrium is reached. If ion product equals KSP, the solution is saturated, and at this point, the solution contains the maximum amount of solute possible, and dissolution is in dynamic equilibrium with precipitation. If the ion product is greater than KSP, the solution is supersaturated. This means more solute is dissolved than should be possible under normal equilibrium conditions, and precipitation is likely to occur until equilibrium is restored. And this framework gives us a powerful way to predict whether a precipitate will form under given conditions. Now, while KSP is an equilibrium constant, there is another quantity we need to distinguish from it, and that is molar solubility. So KSP represents the equilibrium between the solid salt and its dissolved ions. Molar solubility, on the other hand, is the actual concentration of solute that dissolves to reach equilibrium in a saturated solution. So it tells us how many moles of solute dissolve per liter of solution. To make this distinction more clear, let's look at our example using silver chloride. We write the equilibrium equation as silver chloride on the reactant side, and we write silver ions and chloride ions on the product side. If we start with only silver chloride and pure water, then initially there are no ions in solution. But as dissolution begins, we can track the ion concentrations using a Rice table. If we let X represent the molar solubility of silver chloride, then at equilibrium, the concentration of silver cations is X, and the concentration of chloride ions is also X. And the equilibrium expression becomes KSP is equal to X times X, which is equal to X squared. From this relationship, we can solve for the molar solubility directly from the KSP value. And this approach, it generalizes to more complex salts as well. If the salt produces multiple ions when it dissolves, then the stoichiometry must be accounted for in the expression. So for example, looking at this table, for a simple salt AB, KSP is equal to the concentration of A multiplied by the concentration of B, and the molar solubility is X squared. For AB2 or A2B, we can write that KSP is either equal to the concentration of A multiplied by the concentration of B squared, or it can be equal to the concentration of A squared times the concentration of B. But the molar solubility, it's just related to KSP as being equal to 4X squared. Then we can do this for AB3 or A3B. KSP is going to be equal to 27x to the fourth power, and so on. Now, molar solubility is important because it is the measurable concentration that tells us how much solute actually dissolves. And together, KSP and molar solubility allow us to quantify solubility limits and predict precipitation in real chemical systems. This table that generalizes these rules for KSP expressions and molar solubility, we get these relationships directly by drawing out the Rice table. So you can go ahead and sketch out a Rice table for each salt form you see here, and you'll be able to reach the molar solubility equation in the same way that we did it for silver chloride. This table just does a good job of summarizing the conclusions you would reach if you wrote the Rice table for each salt form. With that being said, let's go ahead and jump into a few practice problems together. The first question asks, which compound is the most soluble and which is the least soluble given the following KSP values? We have calcium carbonate with a KSP of 1.0 times 10 to the negative 10. We have magnesium hydroxide with a KSP of 1.2 times 10 to the negative 11. We have aluminum hydroxide with a KSP of 3.3 times 10 to the negative 33. And lead sulfide with a KSP of 3.0 times 10 to the negative 28. To answer this, we can't just compare the KSP numbers directly. We need to solve for molar solubility X in each case. So for calcium carbonate, it dissociates to calcium and carbonate in a 1-to-1 ratio. So KSP equals x squared. That means x is the square root of 1 times 10 to the negative 10, which is 1 times 10 to the negative 5 molar. For magnesium hydroxide, the ratio is 1 magnesium to 2 hydroxides. That is a total of 3 ions, so KSP equals 4x cubed. So x cubed equals 1.2 times 10 to the negative 11 divided by 4, which is about 3 times 10 to the negative 12. The cube root gives roughly 1.4 times 10 to the negative 4 molar. For aluminum hydroxide, it dissociates to 1 aluminum and 3 hydroxides. KSP equals 27x to the 4th. Set 3.3 times 10 to the negative 33 equal to 27x to the 4th, and x comes out to be about 3 times 10 to the negative 9 molar. For lead sulfide, it's a 1-to-1, so KSP equals x squared. That means x is the square root of 3 times 10 to the negative 28, which is about 1.7 times 10 to the negative 14 molar. Now, let's rank them. The largest X is magnesium hydroxide at about 10 to the negative 4, so it's the most soluble. The smallest X is lead sulfide at about 10 to the negative 14, so it is the least soluble. So again, magnesium hydroxide is the most soluble and lead sulfide is the least soluble. So that's how we solve this problem. The correct answer is B. The second question asks, what is the molar solubility of cadmium phosphate at 18 degrees Celsius if the KSP is 1.08 times 10 to the negative 33? Let's write the dissolution. Cadmium phosphate dissolves into 3 cadmium, 2 plus, and 2 phosphate, 3 minus. If X is the molar solubility, then cadmium is 3x and phosphate is 2x. KSP equals the product of concentrations, so it is 3x cubed times 2x squared, or 108x to the 5th. Set that equal to 1.08 times 10 to the negative 33. Then you're going to divide both sides by 108, which gives 1.0 times 10 to the negative 35. Now solve for x. Take the 5th root, which is the same as raising to the power of 1/5. That gives x equal to 10 to the negative 7. So the molar solubility is 1.0 times 10 to the negative 7 molar. With that, we've completed these practice problems, and we can now move into our next discussion on the common ion effect. The common ion effect describes how the solubility of a salt is reduced when one of the ions it produces is already present in the solution. And this idea is really just an application of Le Chatelier's principle. Remember, if a system at equilibrium is disturbed, it's going to respond by shifting in the direction that counteracts the change. Let's look at a concrete example. Consider magnesium phosphate dissolved in water. The equilibrium can be written as solid magnesium phosphate in equilibrium with 3 magnesium ions and 2 phosphate ions in solution. The KSP expression for this salt is the concentration of magnesium raised to the 3rd power times the concentration of phosphate squared. Now imagine we go ahead and add a source of magnesium ions like magnesium chloride. As soon as more magnesium ions are introduced in the solution, the system senses that one of the products has increased. And so by Le Chatelier's principle, the equilibrium shifts to the left. In other words, instead of dissolving, the solution now favors precipitation. more magnesium phosphate solid forms, and the overall solubility of magnesium phosphate decreases. So the takeaway is that when a common ion is already present in solution, the solubility of the salt decreases. You simply cannot dissolve as much of that ion. And this effect, it has several important consequences. In precipitation reactions, it allows us to predict when a solid will form upon mixing two solutions. In buffer chemistry, the common ion effect is what stabilizes pH when a weak acid or weak base is paired with its conjugate salt. And we're going to see that in later lectures and reaffirm it some more when we get to acid-base chemistry. Now, when you're asked to calculate the solubility in the presence of a common ion, the procedure is really straightforward. So first, you want to identify the common ion and the insoluble salt. Second, you're going to write the KSP expression for the insoluble salt. Third, you're going to substitute in the concentration of the common ion directly. Finally, you will solve for the concentration of the other ion, which gives you the new molar solubility of the salt under these conditions. So let's apply this idea to a practice problem. This one says 0.1 molar sodium hydroxide is added to a saturated solution of magnesium hydroxide. What is the new molar solubility of magnesium 2+ if the KSP for magnesium hydroxide is 1.2 times 10 to the negative 11? I'm going to start by writing the dissolution that sets the equilibrium. Solid magnesium hydroxide is in equilibrium with magnesium 2+ and 2 hydroxide ions in solution. The KSP expression is the concentration of magnesium 2+ times the concentration of hydroxide squared. Next, I identify the common ion. Sodium hydroxide is a strong base, so it provides hydroxide directly. Its concentration is 0.1 molar, and so we're going to have 0.1 molar concentration of hydroxide ions present. So before any additional dissolution of magnesium hydroxide, the hydroxide concentration is already 0.1 molar. Now I set up the Rice table. We're going to let X be the molar solubility of magnesium hydroxide in the presence of the common ion. So at equilibrium, magnesium 2+ will be X, hydroxide will be 0.1 plus 2x because 2 hydroxide ions are produced for every formula unit that dissolves. Now notice that we always write these changes as plus x and plus 2x because the equilibrium is expressed in the forward direction, in the dissolution direction. I want to be very clear here that the shift towards precipitation that's caused by the common ion effect, it doesn't change the way we set up the table. It's just going to have the consequence that the equilibrium solubility X is going to come out very small because of that common ion effect. I will go ahead and plug those into the KSP expression. 1.2 times 10 to the negative 11 equals X multiplied by the quantity 0.1 plus 2x squared. Here I'm going to use the 5% approximation rule. The rule of thumb is that if the correction term is less than about 5% of the initial concentration, you can safely neglect it. And what can guide using this rule is by comparing the KSP value to the initial value we had, 0.1 molar for hydroxide. The KSP here is so much smaller, less than 5% of the starting 0.1 molar concentration. So I feel pretty confident using the 5% approximation rule. And of course, we can double check that we approach this correctly at the end when we solve for X. So I'm going to go ahead and replace 0.1 plus 2x with just 0.1. And that simplifies the math to 1.2 times 10 to the negative 11 equals X times 0.1 squared. Now I'm going to solve for x. 0.1 squared is 0.01. I'm going to divide KSP by 0.01, and x here equals 1.2 times 10 to the negative 11 divided by 1 times 10 to the negative 2, which is 1.2 times 10 to the negative 9 molar. I quickly checked that the approximation here was valid. All right, x is very small. 2 times x is about 2.4 times 10 to the negative 9, which is negligible compared to 0.1. So the approximation holds. Therefore, the new molar solubility of magnesium 2+ in the presence of 0.1 molar hydroxide is 1.2 times 10 to the negative 9 molar. And with that, we've completed this problem, and we can move into our last and final topic for this lecture, which is about selective precipitation. Imagine we have a solution that contains more than one type of cation. For example, silver ions and lead 2+ ions. If we begin to add chloride ions to this solution, both of those cations have the potential to form insoluble salts, silver chloride or lead 2 chloride. The question then is which one will start to precipitate first? To answer this, we need to realize that each salt has a threshold anion concentration at which its ion product just reaches KSP. At that point, precipitation begins. For silver chloride, the KSP expression is the concentration of silver times the concentration of chloride. If we rearrange, the threshold chloride concentration equals KSP divided by the silver concentration. For lead 2 chloride, the KSP expression is the concentration of lead 2+ times the chloride squared. Rearranging the threshold chloride concentration is the square root of KSP divided by the concentration of lead. So what we're really doing here is we're comparing the cutoff values of chloride that's needed to initiate precipitation for each salt. The salt that requires the smaller chloride concentration is going to reach its KSP first, and that is the salt that precipitates first. This is the essence of selective precipitation. So by controlling the concentration of the common anion we add, we can force one salt to come out of solution while the others remain dissolved. And this principle is widely used in analytical chemistry to separate ions from mixtures and to design stepwise precipitation schemes. Of course, to solidify this understanding of selective precipitation, let's solve a practice problem together. So this one says a solution initially contains 1 molar silver ions and 0.1 molar lead ions. If sodium chloride is added to the solution, which cation is going to precipitate first, and how many orders of magnitude separate the concentration of chloride ions at which the precipitations start? KSP for silver chloride is 10 to the negative 10, and for lead chloride, it's 10 to the negative 5. So the solution starts 1 molar silver ions, 0.1 molar lead 2+. We're going to be adding chloride from sodium chloride. Each possible solid has a chloride threshold where its ion product just reaches KSP. The salt that requires the lower chloride concentration will hit its KSP first, and it's going to start to precipitate first. For silver chloride, the KSP expression is the concentration of silver times the concentration of chloride. We're going to set KSP equal to 10 to the negative 10. That is the value we have. Now we're going to plug in the silver concentration of 1 molar. That gives 10 to the negative 10 equals 1 times the chloride concentration. So the threshold chloride concentration for silver chloride is 10 to the negative 10 molar. Okay, what about for lead 2 chloride? For lead 2 chloride, the KSP expression is the concentration of lead 2+ times the chloride concentration squared. We're going to set KSP equal to 10 to the negative 5. We're going to plug in the lead concentration of 0.1 molar. That gives 10 to the negative 5 equals 0.1 times the chloride concentration squared. We're going to divide by 0.1 on both sides to get 10 to the negative 4 equals the chloride concentration squared. Then we take the square root and you get a threshold chloride of 10 to the negative 2 molar. Now we compare. Silver chloride needs chloride at 10 to the negative 10 molar. Lead 2 chloride needs chloride at 10 to the negative 2 molar. Since 10 to the negative 10 is much, much smaller, silver chloride reaches its KSP first. So silver ions precipitate first. The two thresholds, they differ by 8 orders of magnitude because 10 to the negative 2 divided by 10 to the negative 10 is 10 to the 8th. So the answer is silver precipitates first and the separation is 8 orders of magnitude. And with that, we've completed this lecture. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.